All right, let's take a look at the number one right here. Now, this one, it's a bit more interesting to work with. Okay, you can go ahead and look at part A first. It says calculate the initial rate of disappearance of BR2 in experiment 1. So the reaction there, or the table there, they give you the initial rate of appearance of NOBR. So if you know the rate of appearance of NOBR and you ask to find out the rate of disappearance of BR2, so you can just relate these two together. So can you go ahead and do it for part A?
Is this like a FRQ from
AP style. So for part A, you can simply use the rate that's provided to you in the table for experiment 1, that it's molar per second of NOBR, but then what do you multiply? 1 mole of BR2 over 2 mole of NOBR. So it should be half of it. So it should be 1.62, right? Just mole ratio. Okay.
Oh, got it.
Yeah. So if they give you the rate of appearance, then you can find out everything. Okay, you can find out everything. All right. It's then for part B. That's the meat right here. It says determine the order of the reaction with respect to each reactant, BR2 and NO. All right. Now I would say this: it is very easy to determine the order for BR2, because what reaction would you consider to find out the order for BR2? The exponent. How do you find the exponents for BR2? Because it doesn't say it's an elementary step. Okay. So without this keyword, there's no green light. We cannot use it. So if you look at experiments 1 and 2, what can you find out?
Well, the initial concentration for NO is the same. And for BR it's double. Yeah.
Uh-huh.
So this is the second order, overall second order.
Overall, wait, hold on. One by one. So we have NO right there to the M power. And then we have BR2 to the N power. So since the K are the same and NO would have the same concentration, so what you would do is to place the rate right here. All right, so N is equal to 1, so we can say, hey, you know what? So for BR2, it's first order.
First order, but overall section.
Well, how do you know?
Oh, we don't know because we don't know the next order. Okay, yes.
All right.
It's so confusing how you're determining that this is first order.
2 is equal to 2 to the exponent.
Okay, but then how do you know it's overall section?
Well, that's, I was refuting. Well, I was questioning. We don't know. We've got to find out the exponent for NO. But now, what's the dilemma right here? The dilemma. Now, for BR2, we pick 1 and 2 because these two concentrations are the same.
Yes, but we don't have the two same concentrations for the for BR2.
So what do we do?
No. Yeah. In the BR2 polynomial. I'm all because for 2 and 3, it's not. There's no pattern. Is there?
Mm-hmm. Now, so the good thing is we just found out the exponent for BR2.
Yeah.
So we can go ahead and say, all right, let's go ahead and look at experiment 3 and experiment 2 because the concentrations for NO are different. So you want to have 2 experiments with 2 concentrations, 2 different concentrations. And since we know BR2 has a, no, they don't cancel out in this case, but we know the, what's, I'm sorry, my bad. I should not rush over here. I simply write down BR2 to the first power, BR2 to the first power. Now they do not cancel each other out because the concentrations are not equal. Okay, so we go ahead, fill in numbers.
But it doesn't matter, right? Like, you don't have to worry about it.
We do, because they don't cancel each other out. So they do matter. The K got canceled out.
Do you never like solve for K unless I'm asking?
Correct. But well, 10 times out of 10, they will ask you. So this is 0.0320 to the m power, 0.0160 to the m power, and then 0.0060, and then 0.024. All right. So what you have is 2 to the m power times 1/4, and they cancel each other out. What is 6.42 over 6.38? That's almost 1. Okay, so 4 is equal to 2 to the m power, so m is 2. So
Yeah,
that
so
means.
the overall order is third order.
So NO would be second order. So now they did not ask for the overall. If you look at the question, it says determine the order of the reaction with respect to each reactant. So you would say that the order of reaction with respect to BR2 is first order, with respect to NO is second order. And show our work, that's all the work you have to show. Okay, so I want to show you this because earlier I said you always hold 2 experiments, look at 2 experiments because they would have one pair of identical concentrations, right? Well, it may not always be the case. And if that is not the case, you would have to find out the easy one, and then you go ahead and utilize that exponent to get the missing exponent. Okay. So after you do that, then you can go ahead and do part C. What is the rate law? What is the rate law?
Oh, right.
All right, so the rate law is simply rate is equal to K times.
AO squared.
And then?
BR to the first.
Mm-hmm.
You don't have to
Yep. All right. So far, so good? All right, now. So, and if so far so good, then I'm going to transition this to another, the next topic. Now, before I go to the chemistry part, of this topic, let me just give you an idea of, let me ask you a question. Let's just say you are at a grocery store and you are checking out. Okay, you're waiting the cashier to check out. Now consider this, you have a cashier that scans the barcodes for all the items, and then you have a bagger to put the stuff in the bag. Okay, so the whole checkout process, it's going to be determined by one of these two persons. So let's just say scanning barcode is pretty easy. Putting stuff in the bag, it's kind of hard. So in that case, who dictates the overall speed of you finishing your checkout process?
The bagger.
Okay, why?
Because the scanning, initially, like, it's easier, so it goes faster.
Uh-huh.
But the bagger is the final step before it gets back into your cart. So if they're not done, then you're not done, and you can't leave.
Uh-huh, good, very good. So does it make sense that we say the slowest step is always our
Bagger.
rate determining step?
Yeah, okay, that makes sense.
Does it make sense?
Because, yeah, without the rating.
Just like if you plan a road trip, the rate or the speed that you would get to your destination, it depends on if there's any traffic. If there is a traffic, it doesn't matter how fast you drive earlier, you're still going to get stuck at the congestion. Right? And now, we are going to look at part E. Okay. Now, what is part E? Okay, let me go ahead and show you. Yeah, so for part E, it shows you a slow step, it shows you a fast step, and we just said what? The slowest step is our rate determining step. Oops, I don't need this. So now, and these little steps is our elementary step. Okay, so these are our elementary steps. So we would say, hey, this is the slow step. Let's take a look at this. And then we say, all right, now let's take a look. If you use the elementary step to write the rate law, okay, so this is the rate determining step. And how do we use the elementary step to write the rate law? Then we'll simply say, hey, you will go ahead and use the coefficient as the rate law. Well, because, well, it doesn't say elementary steps specifically. Here's another word that would imply that these are elementary steps. It's called the mechanism. Mechanism is like the multi-step process, right? You have the cashier, you have the bagger, and that is a slow step. So you would always look at the slowest step to judge the rate law, and you go ahead and write down the rate law like this, and you would say, is this mechanism consistent with the given experimental observation? And we say, no. Okay, but you would say that's the rate law from the from this proposed mechanism would have this rate law, while the actual rate law from the experiment is this. We always determine the rate law from experiments. And from there, we backtrack to trace the mechanism of the rates law. Now, this is the most common kind of question they will ask you, is to see if you truly understand that you look at the slow step as the rates determining step. Do you understand that you would use the coefficient of an elementary step to write the rate law? And then you would say, hey, are these two equal to each other? If they're not, then your proposed mechanism is not a good one.
How hard college is, I feel like our AP classes like accurate reflections of college courses and hardness. What do you say?
AP-CHEM is easy. College Chem is also easy. Yeah.
Like, what? AP classes are not that hard.
Well,
College is definitely harder, right?
well, that is a very interesting question because it varies.
But people who go to Clemens have said that their college experiences are way easier than their peers. They feel better prepared.
Again, it depends on what professor you take.
Yeah, it also depends on.
But
yeah,
in general, it's better because of the ridiculousness of the work that we are doing at school.
Yeah, and also like I mean the environment. And stuff.
Yeah, but it's not universal because I have heard people, I would say it's very fair that the more work you put in now, the easier you enjoy. Yeah. But for people who are simply trying to get an A and not really learn, they're gonna pay a price later on.
Correct.
Yes. All right, so that's the end. Now, that's the end of the rate law stuff like this. However, I would like to show you something. Let's go ahead and try to, let's take a look at number 2.